right. So I'm going to start with a little review, which I always like to do, and then branch off from that. So just to remind ourselves, we have this model of a morphology column. Why isn't it? I want this morphology column here. And but one of the basic features is in layer 4, you have these static features that are at different locations. We pull them to get an object. Lately, we've been thinking this is the object state. So it's not like stapler. It's like stapler open or stapler closed. That's the morphology that we're looking at right now. And we've talked about two different projections from it, from layer 3. One is for lateral to other columns that are observing the same object. So if another column is trying to infer the same object, then they can vote on the object state. That's our voting thing. But the exact same neurons can project to another region, hierarchical, that's observing a different object. So this would be like if this object here is the mug, is the logo, and the upper object is the cup, then it can associate the logo with the cup. So the exact same neurons, the axon splits, and then we decided. And so we've had these two sort of, we've really focused on these two up to now, and as a sort of a primary output of a column. I'm not talking about moving the sensor yet. Now, recently we've introduced a behavior model, which we're currently thinking is exact same function as the morphology model. These are the same column, just like we were talking about earlier, the same column, even though it's doing something different. And the difference is because here in the behavior model, instead of static features, we have changing features. So this model only gets invoked when something is changing. It's static, this model doesn't get invoked. If something's dynamic and changing, this model gets invoked, but the morphology model doesn't. So, so then we had this idea that, and we haven't really worked through all this, so I'll just be careful about this, but that you would pool these same features and you'd have like a behavior. And we talked about, the behavior would be like the hinges, the staple is opening or stapling and closing. I think there's something equivalent to a state, whereas, if I'm observing the stapler starting to open, I don't know it's going to open all the way. All I can know is that it's currently moving in a particular, hinge-like motion. And so that's somewhat equivalent to like the state over here. It's like these changing features don't, this can only represent the current sort of flavor of that thing. Again, because the stapler may or may not go all the way up. It may go up a little bit, down a little bit. And so I need to recognize all those behaviors. So to me, I was thinking more like this is like a behavioral state. It's like the stapler is moving up as opposed it's moving to a destination, which it might. But anyway, we have the same problem. We have to do some sort of voting because we have all these models. If on this view, there's lots of different columns observing different parts of the world, and each part is seeing, something might be moving, like the different edges of the stapler are moving. No one column observes that. And so if we're going to quickly infer what the behavior is, we have to have some sort of lateral voting. We haven't worked through the details of this, but it's a little tricky. I've been thinking about this last week, understanding what these behavioral states are, and we've already acknowledged that we don't really know how we can learn this in real time because we don't have a chance of the object is moving. We don't have a chance to move sensors over everything, but we're still going with this idea. Okay, so I'm just pointing out it's not complete yet. It's unclear if there's a hierarchical component to behaviors. I'm just going to leave that as an open question. I don't want to spend time on it today. But what I do want to do, which is what we talked about on Slack in our focus week, is at least on Slack, we've made the following proposal that we were asking how it is we can associate something like turning the light switch on with the light going on. And what I realized is that when you think about some, like a cause and effect, you're always associating a behavior with another behavior. That is, imagine turning the light on. Well, the behavior is not just there's a switch, but the switch is turning into an on state. And it's not that the light is on or off, the light is turning on or the light is turning off. It's not, so we're associating a behavior in one part of the world with a behavior in another part of the world. And there's always in behaviors like in this kind of, chain of actions, it's a causal relationship, like the light switch goes up before the light comes on. So the proposal was we take these same behavioral states, like something is moved or is moving, and we have to broadcast that generally long distances in the cortex, because we can associate a behavior in one object with anything else, like the association between behaviors. The light switch could be on the lamp, the light switch could be on the wall, the light could be in another room, the light switch could be on a remote control. A light switch could be turned on by talking to Alexa. So there has to be a general way of associating any behavior in one part of the world with another behavior in the other part of the world. And I don't have a picture of this, but the idea was that you take a state in one column or a region, and then you propagate it, and it goes to layer one, so you can associate the next state of behavioral state with the previous behavioral state. And so I don't show it here, but it would be layer one. There'd be synapses going up to layer one, which branch out up here. And so a particular model would say, oh, I'm going to form synapses. If I become active, like the lamp goes on, I will form synapses, whatever was happening previously, which was the switch went up. So that's the basic idea. And there's a lot of evidence that some layer one synapses, maybe all of them, but some layer one synapses at least, are good. They have the properties we want, that they are temporal sort of causality detectors. Like you have to, in order to form a synapse, the previous event had to occur right before this event, and so on. So this is just sort of putting this in this picture here, what the general proposal was. And I'll stop there for a moment if anyone has any questions about it before I get into some more details.
The layer one connection, that's only necessary for knowing predicting the next state if the next state is represented in a different column, right? Like if it is in the same column, we can still just use HTM-like mechanism in.
You could, but that would require, right. I mean, this little vertical line here doesn't mean it has to be out. I mean, it basically means this cell here would literally probably, I don't know, actually, I don't know, but it might just project literally up to layer one and then start spreading around. So it could form synapses in its own column. This is,
so you're saying even for learning the behavior within a column, like just the stapler opening and closing behavior, it would go through layer one?
No, what we're trying, we're not trying to learn behaviors. We're trying to learn causal relationships between two different behaviors. Right? We're not trying, this is not learning the stapler's going up. This would be like, the stapler goes up when I push a button on the wall. Or
so the two behaviors are represented in two different columns.
They might be in the same column. I'll show it down here. This is a picture. Let me just jump to this. This took me a while to understand. Imagine this is your cortex. This is the whole cortex here. Okay, I'm showing you there's some cortex that's recognizing objects and some parts of cortex recognizing behavior. It could all be one modality. It could be multiple modalities. It doesn't matter. You could, for now, assume it's one modality. And this is the world, and we're attending to some part of the world, right? So the cortex, when we're attending to that part of the world, these columns are gonna say, oh, there's something there. Let's say it's a switch. I put in there, there's a switch. So the object can say, and the behavior might say, oh, the switch is going up. A moment later, time two, the exact same columns, it's the same cortex, is now attending to a different part of the world. Now, not every column here is going to be active, and not every column here is going to be active, but if I'm attending visually to this area, and then I'm attending visually to this area, the same V1 columns in the fovea are going to be excited. But it doesn't have to be that way, but it could be that way. So we're really looking at progression through time here. we have the cortex at time 1, we have the cortex at time 2, and the cortex at time 3. And every time you attend to some different area in the world, the columns say, oh, what objects is there and what activity is going on in that spot. So literally the same columns that are active recognizing the switch here would be the same columns recognizing the light here, or they might not be, but they could be. You know, if I'm looking at it visually, then probably there would be many of the same ones would be active. I could be hearing a sound over here, which you know, or something like that, which tells me that the light's going to turn on. So this could be auditory columns, this could be visual columns. I could be you touching the switch and looking at the light. So it doesn't really matter. The cortex has observed something in the world, some object, and potentially some object and potentially some behavior. And then a moment later, it attends to a different space and it perceives a different object and potentially some behavior.
So like even if it's within the same column, like if it's a vision, you're looking at the switch and then at the light, within the same column, you're not in the same object's reference frame anymore. Like at first you were recognizing the switch and then you're recognizing the light.
Right.
So
but it's the same columns, right? It's the same column.
Yeah, same column, but you couldn't use basic sequence memory within that object's reference frame to learn the sequence. So that's why
you can't learn sequence memory because the causal associations can be very far apart.
Yeah.
Right? They're far apart in space. They're far apart. The different objects. They're different modalities. Again, you know, I can flip a switch with my finger, or touch something with my finger, which has no visual impact on the object. But then I don't know. It could be anything. So that was the first assumption that we had was because you can associate anything with anything, then this signal, whatever the causal relationship signal is, like, has to be broadcast broadly. It has to be available to anyone who might be able to I don't know, maybe it's obvious, I've said it several times already. So you can't use the local temporal memory. In fact, I don't think I've asked myself, could this relationship going through time like this, could it be high order? Meaning, and I don't think it can. That is, I can't, well, I'll leave that aside. I'll leave it as a question. One of the things we get from learning, if we learn sequences within a column, we have these high order representations of the elements, and therefore we're able to learn high order sequences. This is not. This is basically an SDR that says switch went on, and then this is one that says light went on. Right? So it's like there's no place I can sort of represent a high order representation of the light going on. It's like it's a singular thing, which kind of makes sense because in the world, it kind of makes sense. I can stop here, or I can just finish this diagram. Then we can talk more about it. Let me just finish this diagram. So we're looking at 3 different time steps here, just to show that this is continuing around time. And as I've argued recently, our life is basically a series of attending to different points in space over and over and over again throughout our waking life. You're doing it right now. Every time your eye moves, every time you're looking at one thing versus another, every time you're looking at this circle, that circle, you're attending. This is happening real time. And as you do that, the cortex as a whole is inferring objects and potentially inferring behaviors. Right? Behaviors aren't always there. I can be looking at my kitchen right now and nothing's moving in my kitchen. But as soon as something changes, we notice that too. Now there's 3 things available to think about. We know what the object we're looking at is. We know what the behavior we're looking at is, if there's a behavior. We also know what the location is, that we know where we attended to in space. All 3 of these can be associated causally with the next event, but it's sort of optional. The 2 things that aren't optional are the object. Well, I'll tell you the 2 things. The location is optional. The 2 things that aren't optional are the object and the behavior. So I'm assuming I can't really recognize the behavior without some object associated with it. So I'm going to see either the switch or I'm going to see the switch operating. I'm going to see the lamp or I'm going to see the lamp turning on. but I would always have the object plus the potential or behavior of the thing I'm attending to. And we also have the knowledge of the location, and sometimes that's useful. Like in my particular kitchen, I've talked about this, we have a pendant lamp over the island, and there's a single switch on the side of the island that turns the light on. Well, I know where that switch is, and I know where the lamp is in my world space. And so when I flip the switch, I know where to look to see where the lamp is, to see if it's turning on. And if I see the lamp turned on, I know where the switch was that someone had just flipped. It's like, I know these locations, but that's not always the case, because sometimes these things move around. I use the example of the remote control. In that case, I have an object, which is the remote control. I have the behavior, which is pressing the button on the remote control. I have the lamp, which is an object and its behavior. Now the lamp is located, it's not moving, but the location of the remote control could be here or it could be somewhere else. So I know that, you know, but in the case of the switch on my island, I always know where it is. It doesn't move. So these things are available to learn causal associations, but we don't use all of them. We don't always use the location one, because I don't always know where things are. I then need to find the object. So if I wanted to turn the lamp on, I first have to find the object that I need, which is the remote control. Then I would know how to execute the behavior, that kind of thing. Anyway, so this is a diagram I think I might be using a lot of in the future, because we haven't really dealt with this before. We haven't really dealt with time. And we have to start thinking about time, about the same set of columns going from step to step to step in time. That is what it's all about for behavior, and that's what it's all about for learning causal relationships in the world and so on. So something along this line, something like this kind of thing is helpful. It was helpful for me to draw this, to get a sense for this. So now if we just assume this is the switch, and then we observe the switch goes on, then the light turns on, which catches my attention. Like let's say I didn't know what it did. I just see this thing and I push on, oh, look, the switch moved. And then all of a sudden this light comes on in the room. Well, my attention will be drawn to that light, subcortical. I haven't learned this yet, right? I haven't learned what the switch does. But this thing happened over here, unexpected change. My attention is drawn to it automatically, subcortically, model free. And I immediately look, oh, what was that? Oh, there's a lamp there and it just turned on. And at that moment, I have the prior behavior and now the new behavior, and I can make that causal association. I can say, oh yeah, well, on my layer 1 synapses, I can associate what was there, with the light turning on, and what was there was the switch turning on. Potentially, and it's a switch, and a switch turning on, potentially at some location. And now, go ahead.
You said object and behavior are both required, but do you need either or both always at the same time? Because that would kind of assume you always need morphology and behavior models to collaborate to learn this.
I asked myself the question, do I need the object model, morphology model? Can I just do behaviors? And I'm trying to think of examples where I just see a behavior, there's no object associated with it. Now, like the motion dot movement is sort of like that, right? When we see the dots moving, and let's say the motion dot, but what happens when I see the dots moving? I imagine the person. I imagine the body. I don't just see it as a pure behavior. The body pops into my mind. It's like the behavior can imply the body. And so I invoke the body at the same time.
Well, yeah, I mean, the behavior is always associated with some kind of morphology, but I feel like you could learn that just the behavior of something flipping it turns a light on. You don't actually you've never actually seen that particular light switch. You have never actually learned the morphology of that light switch, but just the behavior of something flipping, no matter what specific morphology it's applied to, you predict that the light goes on.
Well, but maybe would I predict the light goes on? I might predict something else would happen. I have a lot of things that turn on in my house and they're not all lights. So it'd be hard for me to say flipping turns a light on. That's too general. Flipping could turn my toaster on. Flipping could turn my tea kettle on, right? There's a lot, I can't make that association. I don't think I do. I thought about this. I could be wrong. I'm willing to be, I started off thinking, could I just learn behaviors, go to behaviors? And in the end, I concluded, no, I don't think so. I think it always has to be a specific object and a behavior and another specific object and behavior. For the reason I just gave you, I can't think of real examples that it works without them.
So in this
Yeah,
case,
I mean, it seems. Oh, good.
I just want to say that they're becoming from different columns now. These
Yeah.
the
We
switch
don't.
and this
We don't know. Not necessarily. We don't know that. Like
I mean, assuming,
I'm looking at the switch and I'm looking at the light. That's the same column.
but the behavior is
But the
represented in a
object
different
and
column.
The behaviors are represented in behavior columns. Right. All right. So so the object. So imagine the. Here's how I view it. Here's a possibility. Imagine the columns that are recognizing objects send their object ID on, across the cortex. We know they do that already. We've already assumed that as part of voting. So, now we're just saying, oh, they're also going to go up to layer 1. And then the behavioral models do the same thing. Assume that they send their output, like this behavior is occurring, and just assume everybody can see this stuff. Everybody,
Yeah.
all columns can see this. And then when another column becomes active, it's going to try to associate. It doesn't know what these axons mean, right? It doesn't know that this axon is an object axon. I don't think it does. It doesn't know that this is a behavior axon. It's just going to try to do an association with them. And I'm saying, for example, on the light on my kitchen counter, it's going to say, oh, well, there seems to be this switch. Always seems this particular switch is the one that is always flipping up, and I'll associate it. And in that case, it's also going to associate the location where that switch. It's going to somehow. It's going to. I don't know how it does that, but I'll leave that off for now. It's also possible.
It seems like. Oh, it seems like mechanistically you wouldn't need to say both object and behavior are required. But in a lot of cases, you would associate both of them with the next state just because they always coincide and they are broadcast widely.
Right. So it's more of a from a mechanistically, it doesn't care, it doesn't know.
Yeah.
But the world is such that I need the object. There's always going to be an object associated with behavior, and it's going to be consistent, the same object. Now, imagine I have 2 switches that turn the light on in my kitchen. So I have to learn that there's 2 different objects. So one time the light goes on and I say, oh, I turned this switch on by the door. And another time I said the light goes on, I turned this switch on the island. I have to learn both of those. They would both work. So the switch on the island would lead to the light going on. The switch on the door could lead to the light going on. My point is, it's not a singular object or a singular behavior. Just imagine these are axons that are floating by, and every time this goes on, it tries to form associations, whatever's up there. And assuming there's enough causality, enough, you have enough things to repeat, then you'll be able to do it.
And in the case where you see a switch that you've never seen before, you just observe the flipping behavior. That might be connected, predicting a bunch of things, like the light could turn on or something else could turn on, and only once you learned the association of the specific morphology can you uniquely distinguish that prediction.
Right. Although I would say it's not predicting anything until that association has been learned. It may not do anything. Or, we may wonder what it does, but I have a light switch in my bathroom. It looks just like a light switch, but it turns on the water circulation pump. It's right next to the light switch. They look identical. So, I can't always, generally if I say, oh, there's a Lutron light switch, I'll assume it's turning on a light, but I don't know. I think the whole thing can be done by associative learning. I don't think there has to be any prior knowledge about anything. I
guess the main thing I'm maybe getting at is the object ID and the behavior ID will be coming from different places. Like they might be recognized in different columns. And then mechanistically, whoever connects to that axon doesn't know, oh, this one comes from a morphology model and this one comes from a behavior model. And it can't say, oh, I haven't gotten an input from a behavior model yet. It can just be like, usually I need to get input from here and here in order to fire.
Right. I think that's right. I agree with what you're saying. I don't think it knows, but I don't think it also can say, I usually get this. I don't think it knows that. It just says, did this pattern match the pattern I had earlier? And if so,
Yeah,
at the
that's what I
moment,
meant with that. It has
yeah,
learned to associate these two.
at the moment, I'm treating that the broadcast behaviors and the broadcast objects are mixed together, and receiving column doesn't know the difference between them. That may not be true. It could be, for example, that a sublayer of 2 represents, it could be that when they arrive, they're segregated. Maybe it could be that the rival behavior, the axons of represented behavior form synapses on layer 2A, and the ones that represent objects form synapses on 2B, something like that. It's possible. I'm not saying that's not going to happen, but at the moment we can see how far we can go with just saying, hey, it's easier if they don't have to be segregated, just mix them together. In Mani, of course, we don't have axons, we don't mix them together, so we would know exactly what they are. So,
yeah.
But in the brain, it's much easier if these things don't have to be segregated.
Yeah, and yeah, I noticed when I looked at the board this morning, I think you removed an error in the top drawing,
Right.
which was the broadcast signal from the object, the morphology column.
I thought it was confusing. So,
oh, okay.
right,
But we would still need that, right?
Well, no. So I originally had a dashed arrow here. And I labeled it temporal causality. And the reason I removed it's interesting. Why did I remove it? I removed it because on its own, an object can't predict the behavior. If I just see the switch, I don't predict the light's going to come on just by looking at the switch. The object itself does not predict the light's going to, it doesn't make, it's not like seeing it doesn't make me expect the light to turn on. Only when I see the switch move do I expect the light to turn on. So this is like static things in the world. And I don't think static things in the world, because they're static, they can't cause a change in the world unless, something had to happen. The object had to appear, the object has to change, the object has to move its location. But just the object being sitting someplace in the world does not cause a behavior to happen. It felt to me like only behaviors can cause behaviors to happen. And I thought this having this extra green arrow here was going to be confusing to people.
But for the mechanism you described below, we would still need to broadcast the object ID, right?
Right. So now that we're talking about it, I see the error of my ways. So, but I think here's the problem with it. Let's just put this over there. And so what I actually did this morning, I had it looking differently. I had it as a dash line like this. And because I was trying to say, like, okay, it doesn't really cause temporal causality. On its own, it doesn't cause temporal causality. Let me just 1 second. I just got a text that might be important. Let me just see if it is. Okay, thank you. It's sort of like it's available, but on its own. So maybe I should have done the following. I should have left this here, saying yes, this projects here, but this I could have said this, on, and it'd be like this, on its own doesn't cause any actions, something like that. Okay, it's up there, but just this itself doesn't invoke a behavior. It can be available to this behavior model to help it says, oh yes, this behavior occurred with that object. So this would be the better way of describing it, I think. Does that address that question?
Yeah.
Does that make sense?
Yes. I think, yeah, I'm not sure if I should bring it up or if it's too big of a tangent.
Sure.
Bring up affordances.
Well, I was just gonna say, well, one of the ideas I had was that potentially that signal to L1 could also be a goal state, like a goal. So in that case, also the morphology model could broadcast a goal, and then whatever receives it can learn kind of causally if I get that goal and I'm in a current state, I'll put this action.
All right. I think we can answer that question, but maybe we let's come back to it because I think there's a whole bunch of things under that which we're going to talk about next. So maybe Tristan, what did you want to ask about affordances? That might be related to it too.
Wouldn't there be something where it's like if you see a handle, it can temporally predict a behavior of lifting
No, it doesn't. Not causally, right?
Okay.
I would be really surprised if I just looked at the handle of my cup and the cup lifted up. I mean, like, what the hell? How'd that happen? You know, what caused that to happen? Nothing in the world changed when I looked at the handle. It was there. It's still there. So my looking at it isn't a change. Oh gosh.
What about if, let's say you have a water tab that's connected to a hose that's further somewhere down the line, and you see that the tab is open. You didn't see it turn open, but it's open. So you predict that the water is flowing around the corner.
Yes, that is true. I think that all works in this. Okay, so what that says is that a state of one object predicts a state of another object, but there's no behaviors there.
Well, the water would have
there's no causal behaviors.
Mhm.
Oh, all right. So I think all this works. I'm going to try to make all this stuff work. So, we imagine here on the right we have the hose. This is the hose. This is the hose running, and there's a hose. I'm looking at the hose, and there's a hose running. There are two states of the hose. The hose well, there's two states. Well, I'm trying to think of there's a right. Let's say there's two states of the hose. There's a hose running and a hose not running.
Or maybe to make it's a bit more artificial, but it might make it simpler. You have a switch on the wall, and then around the corner, you have a wheel that starts spinning when the switch is turned on.
Okay.
So as you flip this, you see the switch in the on position. You predict to see the wheel spinning around the corner, even though you haven't seen the switch flipping or you're not seeing the wheel right now.
All right. That's a good example. I think what you're only arguing is that this case here with the dotted line actually, it does work. You could say,
yeah, I guess I'm trying to make it as general a mechanism as possible, like avoiding to say, oh, morphology models don't have this output, but basically anything can have causal connections if that's what you're observing in the world.
Right. It's a little complicated because what I would argue, let me just change this to what I always argue, these are kind of corner cases in the sense that there is no change in the behavior of the wheel spinning, right? Just seeing the switch in the on state doesn't cause the wheel to start turning. The wheel's already turning. So this introduced the idea there's an object called the wheel, which is it is moving. It's exhibiting a behavior, but the behavior didn't start by looking at the object. It's like I need to be able to represent objects that are continually moving, and not like starting to move or stopping to move. It'd be like, okay, so the wheel is spinning, and I could see the state of the switch is associated with the wheel spinning, or the state of the switch is associated with the wheel not spinning. But it's not causal in the sense of one action led to the other action. It's more like
Yeah,
I
more
don't know how
like
to
the
describe it.
states are connected. When one is in one
Right,
state, the other
right,
is in the other
right,
state.
right.
Yeah.
I think going back, Tristan, your question, you know, when we talked about behavior models earlier, when we first came up with them, we know that behavior models can be associated with morphology models, right? We observe a behavior, and when we observe it, we are on some object and some part of some object. And so we can associate those two. So if I look at, let's say the switch, I know I immediately see, oh, this switch could go up. I know the switch could go up, it could go down. And so for that to occur, I imagine that the object of the object model would be at some location on the object model would be linked to a particular behavioral state or behavior. I think you know, this is all these flavors of this. It's just like we had all these flavors of compositionality, and we kind of had to make a list of them, and then we said, okay, do we have a mechanism that solves them all? I haven't made that list, but I think I have a mechanism that solves them all. If that makes sense. I think with some tweaks, this basic idea can solve all these problems. I mean, I'm not saying it's all 100% done, but essentially this idea that there's another projection which is only useful for causality, and then beyond that, everything else is, you know, is coincident associations. So this is like an association in time, and these are associations that aren't in time. Oh, I should go back to my little cursor. These are associations that are not in time, and these are associations that are time-based, or, you know, causally based. And then we could go through, like, you know, what does it mean to have an affordance? So how do I associate behavior model with a morphology model? What does it mean to have a morphology model with a continuous behavior? We never really asked ourselves what's a continuous behavior model. I don't see any reason why it couldn't work that way.
On the topic of associating behavior with morphology, I thought the remaining dashed arrow is the one that we could also use for that, basically associating a behavior ID with the location on morphology.
Right. I guess when I put the dash line here, I was thinking purely about the temporal causality projection.
Oh, okay.
Like, not like this behavior is part of a switch, more like this behavior is a child of another behavior, which is a child of another behavior. So
okay.
Again, right. So let me just do what you just suggested, because I think that's correct. We'll make these solid, just like I did before in the other one. And then I'm going to change the text to say, all right, hierarchical composition, behavior to object. Yes.
Yeah.
Behavior to behavior, question mark. How about
Yeah.
that?
Yeah.
Okay.
I like this picture now because it's like the same exact mechanism for both, and whether a connection forms or not really just depends on the statistics
Right.
of your environment.
Right. When I wrote this diagram, I was trying to figure what parts of the system I'm going to show. And I started off by thinking, like, I really just need to show the behavioral component, like how the behaviors get propagated. And then I started adding some objects things, and I said, oh, and I just didn't go all whole in. So, which is what you're suggesting, which is right. Right. These are identical, but there are some caveats, right? Right. As we said here, just observing an object doesn't cause any actions, but it could. I could associate one object in a state with another object in a behavioral state, right? Where the thing is spinning, like.
Yeah, or
Yeah.
use it as a kind of conditional causality, like in the example below. You need both a behavior and an object to predict the next state.
Right. Hopefully, again, hopefully columns that can just, they can just associate whatever makes sense to them and it'll work.
Yeah.
All right. Yeah. So this is the basic idea. I didn't show a, maybe it's worth going back to the picture of the pyramidal cells here. This complicated diagram, we're talking about these synapses up here, and of course, there's the relationship, the apical synapses with the basal synapses, they're not treated the same. It's believed that you can recognize a pattern up here in the same way you recognize a pattern on here, but the effect on the body of the cell is different when you detect up here. And there's a whole bunch of complicated rules which I've forgotten about. This generates a calcium spike and the timing issues and so on. So there's a complex mechanism between what happens when these guys go down here, and of course there's a back propagating when the cell body fires. It sends a back propagating signal up here. So the basic idea when the cell fires, it sends this back up here, and it sends it back up here. And the theory is then you'd say, oh, form synapses to whatever pattern was there a moment ago. It's not there now. That pattern's gone because it's a behavioral pattern. If it's a behavior, it's gone. The behavior's, I'm not looking at that behavior anymore. I'm looking at something else. I'm looking at the lamp going on now. And a moment ago, I was looking at the switch going up. So the moment ago, the switch going up, and now I come back and say, oh, we activate these cells, which means lamp going on. And only if the switch going up was prior to the lamp going up would you form those synapses. If you came up here and the synapses representing the lamp going on had been active for a long time, it wouldn't associate the two. So there's a time-based, very specific time-based requirement here that these synapses only form when the previous behavior existed and is now gone, and we have the new behavior. So I can associate the new behavior with the previous behavior. And of course, we just walked through a whole series of complications about objects and behaviors, but that's the basic idea.
I have a question about this window of temporal causality. Is there an assumption here that B2 has to be right after B1? What if we have like B1 and then some other behavior that could change? There's no causality there, and then we have B2. Are we not able to form associations between B1 and B2 if there's something that's happening in between?
Yes and no. And so I remember I talked about this sort of chain. The last post I put in Slack was about you can have a series of events that lead to something happening, and then you want to reinforce that series. But let's take a simpler example. Let's say I have two light switches, and one of them turns on the light, but after a delay. And I flip that switch up, the light doesn't come on. Then I flip another switch up and the light comes on. I am not going to associate the light going on with the first switch, even though that really is the one that caused it to happen. I'd have to do a bunch of experimentation where I flip the switch up and wait and then see the light comes on. Then I say, I think that's possible. There's some amount of time you could sort of, that's how dopamine works. You have to be anticipating the reward, meaning the light going on, and as long as you're anticipating that reward and the previous thing happens, and there can be a delay, but as long as you're anticipating the reward, you can form the association. If you switch to another anticipation, like if I flip the switch on and the light doesn't come on, and then I go attend to something else, like I want to turn on the coffee pot. Well, when the light goes on, I don't think you wouldn't be able to, I pulled out the coffee pot. I wouldn't associate the switch with the light. I think we'd have to walk through it. The short answer to your question, Rami, I think, is a time delay can be acceptable up to a certain point, but a series of distractions between the event and the causal event and the action is not going to be learned. It'd be very
It feels
difficult.
like we manually have to maintain that L1 representation so that we can associate with it.
I don't know if you have to maintain it. There was this. I talked about this. There was this idea of these trace synapses. I don't know what the word they use for. It might be that word. It might be something else. But there are papers on this. At least one, because I remember that. That showed that when an incoming axon fires, and it doesn't, and then it puts a synapse into this state that's primed to learn. Right? It's not learning yet. It's primed to learn. It remembers. These synapses are all active. They don't have to be active now, but they're in this primed state. And so when the learning signal comes up, only the primed synapses get learned. So that would suggest in biology, not necessarily Monty, but in biology, the representation of the behavior is no longer there. It's gone, but it's remembered in these trace synapses. And then, right. And this was important too, because we talked about how to solve a problem, you might have to do a series of actions. So let's say I don't know. I'm trying to think of an example here. I don't know how to. I want to get. I want to turn on the coffee maker, but it's behind this little flipper door I have. So I can't just turn on the coffee maker, and maybe the flipper, and so I'm experimenting, saying, "Oh, how do I get to the coffee maker? Oh, I have to lift up the lid, then I pull the coffee maker out, and then I can push it on." Well, a series of events. I'm not sure that's a good example, but the idea is a series of events could have occurred that were necessary to turn the coffee maker on, and that series would all be primed. And so if I now reward the signal, I have the reward signal, the goal has been achieved, then all the prime synapses for a series of prior behaviors would be reinforced. As long as you're all in the same sort of anticipatory period. I'm anticipating this thing happening, and if I have to do several different things to make it happen, they'll all be reinforced. You might learn a local minimum. You might have done 3 steps and you only need to do 2. You didn't know that, but you're going to learn. This is how I did it. I did A and then B and then C, and the thing happened. So that's how you'd learn it. You learn that sequence.
And yeah, for more kind of long-term causality, I think it's also a pretty conscious process that's also pretty error prone. Like, for example, if you got a good grade on a test and then you kind of need to think back to the past. Okay, what did I do differently this time? And you think, oh yeah, I studied more and I also did this weird superstitious thing. And then the next time you write a test, you might test your hypothesis of like which one contributed. But anyways, like you kind of go back to your memory of the past and then maybe replay those events and then associate those as potential causes.
That's more like an episodic memory, going back and replaying episodic memories, which I'm not addressing here. That could fit on top of this, right? Because you can replay it.
Yeah, I don't think this mechanism works for very long time scales, but for the longer ones, we could use episodic memories.
Right, just replay it back and over and over again.
Yeah.
Any more questions on that before we go into the next topic here?
Maybe does the hierarchy here plays a role in this longer time scale thing where if we basically build higher order sequences of these behaviors, can they build associations in a higher order easier than they would do at a lower order where there's a lot of distractions between the behaviors.
I don't
don't
know. That gets back to this question here, I guess. You know, this one here about,
Mm.
you know, whoops. Oh gosh, what is it? You know, are there hierarchical, you know, behaviors?
Yeah.
I think for the moment, I think we should assume not. At the moment, I think the way to think about this is, and I've come to think about hierarchy imagine hierarchy in the morphology model. I've come to think of it differently than I used to think of it. It's like you have all these visual columns in V1, V2, and V4. They're there just so that I can infer whatever object I'm looking at. They all have it's a single output. What object am I looking at? And by having multiple regions in a hierarchy, it allows me to learn compositional structure, but I don't rely on the hierarchy to recognize compositional structure unless I'm having trouble. Then I can go and attend to individual components. But in general, the whole goal of the visual hierarchy is to output a single thing. This is what I'm looking at right now. And I want to do it quickly. Therefore, I need lots of columns in a region. That lets me do it quickly. And I want to be able to learn highly structured objects, compositional objects, and I need a hierarchy to learn that. And also to infer it if I need to. So if inference is too hard, I might rely on going back and looking at the components. But the goal of this is always to output a single thing. It's not really hierarchical processing. It's more hierarchical learning, hierarchical compositional models. But in the end, when the brain attends to some spot here in space, I'm going to get one answer. What's there? And so you can sort of compartmentalize the hierarchy into this, even across modalities. It doesn't really matter. It just says, the top of the brain, the hippocampus or the prefrontal cortex says, what's in this space? And all the columns and the regions below are trying to get to that answer really quickly and said, oh, that's a car. Or, oh, that's a letter A. Or whatever the attended space is. You know, that's a new word I don't know. Therefore, attend to the letters. Okay, that's a B type of thing. So that's my new thinking about hierarchy. It's in the end, I can just say it's producing one thing, and if we follow that example, then the behavioral, if there's a hierarchy in behavior, like the MT type of things, if there's a hierarchical processing there, it would be along the same lines. It would be like, okay, what object is here and what behavior is here? And that's the single answer I get. And now I have that single answer. I can attend to another spot. I get another single answer of any kind of complexity, but I don't know, get another single answer. And then I can associate those two things. So, and that's why I showed this picture here. I showed the object as one rectangle because inside of here is the hierarchy and all the regions, and it's like this is not one region. This is the entire. This is really the entire cortex that does morphology modeling, touch, and vision and hierarchy and many columns. It says, okay, what's in this space? What's the action in this space? What's in this space? What's the action in this space?
Yeah.
That's a big change. If it's not obvious, that's a huge change in a clarity in my thinking, at least in my thinking. If it's right, it could be wrong. It's stupid, but it feels right. It feels like, yes, that makes sense. It's like I go about the world, I'm looking at object location, object location, object location, object location. I'm only aware of the one thing I'm looking at this point in time. All the rest of it's still there, but I'm attending to one thing at a time. And as I do that, it sort of feels like I'm looking at everything, but I'm not really. All right. Do you still have questions about that, Rami? Was that helpful?
No, I think that's helpful. Yeah, that's good enough.
Did you want to say something, Vivian?
Yeah, I was just gonna say, yeah, I really like this mechanism, and it seems pretty simple but really powerful. And yeah, I was just wondering, instead of behavior, can we also use like object and action output to then make a prediction about the next state? Like, let's say I'm sensing stapler in a certain state, and now I'm applying pressure to it, and I want to predict how it will look like the next state.
Right.
That
I
would use the same mechanism, right?
well, probably. I didn't want to go there yet. This is confusing enough looking at it this way. Obviously, the goal of this, in some sense, we have to figure out how the cortex generates behavior to make these actions occur. Some of them, like I have to do a physical behavior to move the switch. I don't do a physical behavior to turn the light on. I'm hoping that if this framework is correct, then it'll become obvious how to attack on behaviors to it. But I have purposely avoided thinking about that right now. So maybe you're thinking about it and you got it in your head already.
Yeah, but yeah, I wasn't even asking about how do we now use this to figure out which action to produce, but just like right now, this is how to go from one state to another state that are causally related, but there's no actual intervention from the agent involved here yet, or observed action. So
No. Well, there's observed action. There's observed action.
the behavior, I guess. Yeah.
I mean, I think it starts with switch going up, and then we have to ask ourselves, okay, well, how do we make that happen, right? Is that what you're asking?
Yeah, I'm not even asking about that part yet. Just like basically, I know my finger is currently making like pressing on the switch. How do I know it's gonna transition into the up state, and how do I know it's gonna turn on?
I'm going to take that out of the picture because obviously, if the switch is going up, it could be any one of my fingers. It could be my knee. Often on our kitchen counter, someone accidentally hits the switch with their hip. Right. So I could press it with a stick. Maybe the switch has a motion detector on it. So my point is, there's this description here. This description is independent of the physical thing that made this happen. And so I feel like I can separate them out completely. And then we can ask later, well, how do physical actions interact with the switch moving? And how do I, in some sense, again, it's like I have to be able to associate, if I want the switch to move, I have to be able to, I can do that with any kind of thing. I can hit it with a chopstick, I could, any part of my body. It has to be sort of a broadcast thing. It has to be like, somehow we wanted this behavior to occur, and it's going to be put out in sort of body space, and as a separate sort of question is like, what part of the body does it? That's independent. Everything I've described here has absolutely nothing to do with who moved the light switch. It's just that this actually did occur, and I'm learning this causal relationship. So I don't want to think about the finger right now. It's like, it doesn't have to be the finger. It could be anything, right? It could be Alexa. I could say, Alexa,
Yeah.
turn the switch up, and then the switch rotates up. So, well, it's a more general.
Yeah, I'm just trying to figure out how actions tie into this picture. Like, no matter which actions you use, like how do you learn to associate like when actions are taken with
when you say an action, you mean like a physical action of the body?
Yeah.
All right. I don't know.
Like your body does something, and how do you then use that to predict what to expect
think if we can get comfortable with this idea, and we have to talk about the reverse causality, and if we like this idea and it seems to work, and we don't, and we kind of explore it a bit, and there's no obvious hole, then I think it'll be a very, very simple exercise. Well, simple. Like, we can then ask the question you want to ask, and say, okay, I have a good mental model of what's going on up here, how I've learned the causality of the world. Now I have to tack on something else about how does my body move things? Because in the end, it's all about, well, no, it's not even that. It's how how is it that I can generate the behaviors that make these things happen? I could use my voice, I could use my fingers, I could use eye tracking. I mean, there's a whole bunch of stuff I could do. So, but that would be the next question. I wasn't ready to do that today, or even this week, or I have to even see if I had to run this by and see if it makes sense. Then what am I missing here, right? That kind of thing. So we're doing that today. We've come up with some good ideas today.
Yeah, I mean, in my mind, like adding actions into this would be pretty straightforward. Like potentially even actions are also modeled as behaviors in the motor cortex and can broadcast the same way to layer 1 and be associated the same way.
That's a great idea. I like that idea. Right. But it's interesting because the action I actually have to take in the motor cortex could be different. Sometimes it's very predictable. Like once my hand is on the light switch, I know automatically how to rock it. But other times, I might need to use some weird extra tool or something. So I think there's a bunch of questions there, but that sounds like a good idea. I mean, so. Right. I think that's the next thing to think about. And that was a good idea to start thinking about it that way. Start thinking about motor cortex. But again, we have to be careful because it could be, auditory. It could make this happen. It has to be a very general mechanism that's broadcast somehow. I don't know.
But how would auditory make anything happen?
Oh, I could just, I could speak a spoken command, or I could clap my hands.
Oh, but that would still be you moving things, right? Like you move.
Right. But my point is, I'm moving my vocal cords. I'm not moving my body through space.
Yeah.
I know. I have to think about it. I think your idea sounds right. I want to think about all the anyway. Right. But can I just finish this up and then we can go talk about that?
Yeah.
Because we had a bit of debate about the question about reverse causality, right? I see the light, and now I want to turn it on. How do I know where to go to the switch, right? Because this arrow is one way, so turn the switch, and now I immediately know. Imagine there's a location for the switch, and there's a behavior and an object, and there's location and object and behavior for the lamp, so I can associate these three things. The switch on the side of the island turning on predicts the lamp on above the island. Switch goes up and the lamp turns on. Great. Now, how do I know when I want to turn the light on that I have to go back to the switch? That wasn't learned so far. And so I had a proposal on that. Let's just change the color. The proposal was that we do learn this as a causal, that this precedes this. And the way we do that is in this model here, I see the light. Let's say I see the light, and the light is associated with the behavior of turning on. And so I'm imagining the light turning on. I'm looking at the light, and I've invoked the behavior of the light, and I essentially invoke the behavioral sequence, not like it's really happening, but it's as if it's imagined. Like, oh yeah, I'm imagining the light coming on. And I'll just see the light, but I perceive the light turning on, like I want it to turn on, or in my head I imagine it turning on. So there has to be like a state here of behavior, like if the behavior happened, but it didn't happen. It's like the behavior I want is the goal. And I've invoked that behavior here, but in a way that this guy locally knows it didn't really happen. I'm just imagining it happened. But it sends this signal back as if it really did happen. The receiving cells over here don't know that the light didn't turn on. For them, from their perspective, it looks like the light turned on because they got this signal. It says, oh, the light turned on. This guy's thinking, I'm thinking about the light turning on. And he says, okay, well, let's send it over here. And this guy says, oh, well, now the switch goes up. So I look at the light. How do I turn it on? I find the switch. I go, here's a switch. Let me turn it up. And bingo, and then the light goes on. And when the light goes on, then this actually really does change. And so there's a release of dopamine, and so these causal connections are going. These are formed. So by looking at the light, imagining it turning on, turning the switch, then the light actually turning on. So I look here, I look here, then I go over to here, and then I go back over to here. I've learned these relationships both ways. But obviously imagining this didn't turn on, but this guy associated with saying, oh, I'm supposed to, given that the light just turned on, I expect my switch to go up. And so it's like, and if the switch goes up, I learned to associate it with. So anyway, imagine light turns on, tells me to look at the switch over here automatically. I know where to look. I know there should be a switch there, and I know that I want it to be in a different state. I want it to be in the state with switches on. So the basic of this reverse causality is that you are propagating in one direction imagined behaviors and propagating in the other direction actual behaviors. But I'm hoping that in the transmission, these two signals look exactly the same. The only difference is in this column, any model here, it says it knows that it didn't actually happen. It knows it was just imagining it. And I think I wrote more about this in Slack. It was more cohesive. I'm having trouble remembering it right now. So this can go. This can go multiple steps. You can go from observation here, imagining. I'm thinking like maybe this. You imagine some behavior here, then you imagine the behavior here, and then the actual behavior happens here. Then all these connections get reinforced. So it's a sloppy explanation for this. I'd have to think about it more. And I'm forgetting what I wrote, but the basic idea is that you actually do learn the reverse correlation because you observed it. You observed the imagining light come on and then the switch going on.
So the green arrows are basically like goals that are being sent down. It's not actual reality, but it's how you want reality to be.
Right, but the receiving column doesn't know that.
Yeah, but then, so I get all the how it will be learned if it's actually accomplished. But how does the receiving column first figure out how to achieve the goal before it has ever achieved it?
How's the receiving column? How does this column?
Yeah, how does the switch column know to flip the switch if it gets the light turns on goal?
All right, so, well, I don't know. Let's just walk through it. It has learned in the past that light turning on precedes switch going up. Okay, because I looked at the light, I turned the switch up, I back on the light. And so this assumed that they learned that association.
Yeah, so I get how it works after it's been learned. Like after I've seen the light go on, after I flipped the switch and had the goal of turning the light on. Like once that connection is learned, that works really well. But does it mean to first learn that connection? It's a bit of like trial and error and kind of random guessing?
No, I think, maybe, I don't know. Let me take a guess at that answer.
I mean, it might be. I don't have a better proposal.
Let's say we learn this black line first, right? We learn this. We have no problems learning that, right? I turn the switch on, the light goes on, I observed it, done. And now you go back and forth over and over again, turning the light switch on, turning the light switch off, which, as we know, young people do. Over and over again. And every time they're looking back and forth. So I don't know. I can't answer your question. I'm hoping that in that process of going back and forth, you're learning this green arrow as well as the black arrow. So you might have to start with the real causal black arrow. Let's see here.
Yeah, I think that could make sense. You kind of do the behavior over and over again, and you have a goal, and you just kind of repeat the actions you recently took to try and accomplish that goal again.
I don't think there's a goal here. Like, I show this to a child. I don't think they have a goal to turn on the light. They're just fascinated that the switch turns on the light. And so they do it over and over again. We can say that the green arrow is sort of represents the imagination of the light going on, but I'm not even applying like an overall goal. The child not sitting there going, hey, it's just like discovery, right? We can discover the morphology of an object without having a goal.
Well, I mean, I think they would have the goal. Like if the light is off, they want it to be on again. If the light is on, they want it to be off again.
But it's not like they're trying to read and they need more light or something like that.
No. I mean, just generally, they just want to change the state. Like, I mean,
okay, so fine.
They just set themselves random goals and
right.
accomplish them.
It's a little bit like moving your finger to learn the morphology of the object. You're going to look for novelty, right? And so it's sort of like here. Oh, I'm going to look for these. I'm going to look. These things here changing. I love when things change. So let me just go back and forth between the changes. The switch goes up. That's fun. The switch goes down. That's fun. The light goes on. That's fun. So in terms, so I don't think there's any overall goal other than it could be. I mean, it could be model-free goal. The goal is just to observe these causalities, and that's rewarding in its own right. And then we might say there internally this module here is saying, oh, I'm imagining the light goes on, so that you can call that a goal. But it's only a goal in that like you're imagining it. And so what happens? What makes it happen? This is what makes it turn on. Something like that.
There may be a role for the trace synapses that you were just talking about, Jeff, where because we just know that the switch going up was just firing, and maybe that makes it more perceptible to like connections coming back in the other way.
Interesting, but I don't. Right? Yeah, I don't. Yeah, maybe. I'm sorry. It's so hard for me to think about this sometimes. I've sort of at the limit of what I've absorbed, and now it starts getting confusing a bit. So that sounds good, Mommy. I can't visualize it in my head at the moment. It's like, yeah, I need some concrete examples. I mean, it's interesting how the lamp switch turned out to be for me a really good example. But the trick for me was to realize that I have to solve the lamp problem in a very generic way, where the switch can be anything, anywhere, and the light can be anything, anywhere. And so it's really just actions to actions, and that also that there is this, it's the same columns that are tending to different regions in space. It's not like, that was a big insight for me too. It's like, okay, it's the same columns attending, the same columns attending. But I think the lamp actually works really well as a proxy for all the things that can be turned on and all the ways you can turn things on, and maybe having multiple steps to turn things on, type of thing.
Yeah,
I'm at the end of my my abilities right here, or the end of what I have to talk about.
I have a question. Like,
yeah.
Why is there a need for green arrows at all? Like when a child learns stuff, they just do all the sequences. So you don't have a switch goes up, light turns on, and then somehow learn the backwards sequence. They will totally observe light is on, switch goes down, light is off, switch goes up. Like
right.
They will. So like when they have a goal, like why is there a need for green arrows?
Because,
they're just gonna enter a different state.
Right. Let me explain it. It's a good question, Tristan. When you go the green arrow, the child doesn't actually observe the light turning on and then observe the switch going up. That actually doesn't happen in that order. The light actually doesn't turn on. They're imagining it turn on. So there's a difference. I don't actually learn that the light turns on means the switch, when the switch goes up, it's preceded by the light turning on. So when I see the light turning on, I don't go over and then imagine the switch is going to go up. It doesn't work that way. So the green and the black arrow are actually mechanistically identical. What's different is I need to show them because green represents a behavior that actually hasn't happened, but we're pretending it happened. It's like, you know what I'm saying? It's the same mechanism. I could have drawn it in black, but there is a difference. The child does not observe the light turning on followed by the switch going up. That doesn't actually occur.
Yeah, I would say the green arrow is really important for figuring out how to actually cause change in the world. So, like in the literature, how people often talk about it is that there's a forward model, which is you have state one, you have you have an action. Oops. And then it learns to predict state two. Like that's the I'm in. And action could be the behavior model in this example. So I have the switch goes up, I predict the light goes on. And then you have the cursor, inverse model or backward model, which is you have two states, state one and state two. In this case, it would be a current state of the world and a goal state. So the light is off, but I want the light to be on. And you need to learn which action to take to move between these two states, if that makes sense. And you can't really do that with only the forward model by itself.
Right. Well, but the action, it's a challenge because, well, in my case at least, because the causal relationship, the mechanism I proposed by the black arrows was only forward. It wasn't inverse. And so,
Yeah.
but by switching to this imagined state two, followed by imagine action two, followed by actual action one, you can learn that inverse model.
Yeah, exactly.
It's
And
nice. It's nice. It's just so many things that are nice about this if it works. If it works.
I guess the essence of my question is, why isn't there a T0 and the behavior is light turns on in the future, and then we go learn forward to T1, and then we learn forward to T2?
Well, that's what it is they're doing, right? I mean, light going on in the future means I'm imagining the light going on.
Right, which would be somehow qualitatively different states than they actually being on, which would be a separate behavior.
Right, I'm saying mechanistically it's the same. By the way, there's something misleading about this drawing I just realized. I hope it's not misleading you. This green arrow here obviously doesn't go from T1 to T2. This green arrow goes from T1 to T3, back to looking at the switch again. We can't go backwards in time.
Okay, that was very confusing. So that clarifies a lot. Thank you.
Right. I realized that was a bad thing on my part. So let's just try it this way.
No, I'm good. That clarifies.
No, I want to get this right. Oh shit! What did I do here? I didn't want that. One thing. I want to do this, and then I want to do copy paste, and then I want to put this up here, and I want to say, okay, now we're like T3. Forget about this one for a moment. This is not happening. We're just going back and forth. T3, object one. So right. So now that's a little bit clearer. You observe the switch goes up, and then the light turns on. I'm not even sure this is T3. This is some. Hang on, just bear with me so I can make this work. T3 is imagining it turning on, and then that goes back to here. Like T4, something like this. Object one, which is a switch. Yeah, something like that. Oh, maybe spell it right. All right, so we're saying you time one, you observe the switch go up, and then you associate the light turning on. Once you've learned that, you can imagine the light turning on, and then you go back and you turn the switch on, or then you associate that is light going on and the switch going on, or maybe imagine light going off and then you imagine the switch going off, something like that.
And T3
Right.
should be at location 2, right?
Right. Something like this. I'm not sure it follows exactly in this order, but it's like, yes, you have some period of time you learn this, 2 sequential periods of time you learn this, and 2 sequential periods of times you learn this. Going back and forth between the two.
Much clearer, thank you.
Yeah, and now you can say, you can imagine someone telling you, "Oh, Tristan, please turn on the light on the kitchen counter or the kitchen island." You visualize that object in your head. You know where it is. You say, "Oh," and as soon as you think about the light, it associates it with the behavior of the switch. Like you have to think about the light first. I say, turn on the light. That's like make the action light going on. Then you attend to that light, and then that invokes the back behavior that says, "Oh, that immediately as soon as you see the light, then it makes you think of the light going on." Thinking of the light going on makes you think of the switch, and both where it is and what action has to be occurred in the switch.